All right, so on Thursday we were getting into more complicated reactions that were multi-step. The example I gave you was a multi-step reaction where you've got starting material A, it goes to intermediate B, and then intermediate B goes to the final product C. So we said that we can draw this on a reaction coordinate diagram, that intermediates are located within wells, but transition states are the peaks of the hills, right? Can we isolate a transition state? No, you can never isolate a transition state. Can we isolate B? Yes, you can isolate intermediates. Somebody was asking me, all right, hypothetically, if we grab B and we bottle it up, and we've got it in our lab, once we have B, we have two different pathways, right? We can either go to C or we can go back to A. Under low temperature conditions, what do you think is going to happen? It's going to go to C because it doesn't have enough energy to overcome EA1, right? What about under high temperatures? A is still higher energy. So in this case, the thermodynamic product is the exact same as the kinetic product here. And oftentimes that is the case, which is convenient for us because you just apply a lot of temperature, the reaction goes faster. But it's important to remember that thermodynamic products are the ones that are most stable or lowest down on the energy diagram. The kinetic product is the one where it has the smallest hill it has to overcome. All right, what do you think the rate determining step is for this reaction? Do you think it's going from A to B or B to C? A to B, why? It's the largest hill you have to climb. So the rate determining step is defined by the largest hill you have to overcome or your largest activation energy. And this is directly related to the rate constant. So in this case, the rate constant has nothing to do with the concentration of B in solution. It exclusively has to do with the concentration of A in solution. And we're going to talk more about that when we get into substitution reactions. But there's also one last point I wanted to bring up. And this is called the Hammond postulate. And the Hammond postulate at first sounds a little bit weird, but I'll write it out for you. It says a transition state, I'll abbreviate transition state as TS, will more closely resemble the starting material, intermediate, or product that is closest in energy. Oops. All right, so if we go back and we look at our chart, let's take a look at the transition state going from part B to C. All right, so we're looking at that green transition state. Do you think that transition state's more closely going to resemble B, C, or A? B, exactly, because the transition state in terms of energy levels is closest to B. It's pretty far away from C and pretty far away from A, too. So the Hammond postulate is basically just saying your transition state's going to more closely represent the intermediate, the starting material, or the product that is closest in energy. It's nothing earth-shattering, but it does make a good assumption when you're talking about chemical reactivity. We're talking about this in terms of generic reactivity right now. It'll make a lot more sense when we actually see specific reactions applied to the Hammond postulate, but I did want to introduce it to you. All right, now we get away from thermodynamics and kinetics, which I'm sure you guys are relieved about. Let's math. We get to talk again about reaction arrows. Reaction arrows don't go away in organic chemistry. And we've already covered reaction arrows in acid-base chemistry, right? So we said if we've got an acid plus a base, this is in equilibrium with our conjugate base. plus our conjugate acid. I want you guys to add in the arrows here. And you only need to do arrows going left to right. I'm not super concerned going the opposite direction right now. Oops, I'm forgetting a lone pair on B too. In this case, we're doing a Bronsted transfer because we're moving a proton. But it's still a Lewis acid-base reaction because all acid-base reactions are. All right, so we said the lone pair on B is going to attack H, and are we done with the proton transfer? No, we've got to break the sigma bond, right? All right, and when we do that, A gets a new lone pair on it that used to be that sigma bond between A and H. That means A's got a negative charge. B's lone pair is now a covalent bond to the hydrogen, so B is now positive. What's the nucleophile? Is it AH or B? B. B is our nucleophile. And AH is our electrophile. Remember, we said that if you're looking at AH, there's normally a net dipole, right? So this delta H is positive. Or sorry, the H has got a delta positive on there. That means it wants electrons, right? So electrophiles, by definition, want electrons. A nucleophile, on the other hand, wants something that's positive or partial positive. It wants a delta positive or a full positive on it. So the one thing I was trying to drive home with acid-base reactions was we always start electron pushing arrows at electrons. We don't show the movement of the proton by having an arrow from a proton going somewhere else. It's always showing movement of electrons. And so typically when we're looking at movement of electrons, we have our nucleophile. Going and attacking our electrophile. And what we call this is just a nucleophilic attack. So let's think about what classifies something as a nucleophile, what classifies something as electrophile. So far we've addressed a couple of them. We said that nucleophiles want a partial positive or a full positive. But what specific features of a nucleophile make it nucleophilic? So let's make a brief list here. So let's say we've got this molecule. Why would this be nucleophilic? Specifically the carbon. What do you think?
Well, lithium it wants to get rid of its electrons, one thing.
Yeah, exactly. So if we look at the net dipole moment here, it's pulling electron density away from lithium, which means carbon's got a delta negative. So delta negative atoms are nucleophilic. Same thing with atoms that have a full negative charge on them. They're also nucleophilic. Let's do the same thing with water. Water is a nucleophile. Why do you think water is a nucleophile? Yeah, it's polars. Just like we said before, this water is got an oxygen that's pulling electron density away from each of these hydrogens, so it's delta negative. What else does it have that we didn't see in the first one? On the right track, the lone pairs are really, really key in this place. So water has a delta negative and a lone pair. So lone pairs are often involved in nucleophiles. The last one that's a little bit less intuitive, I'm going to draw with bond line structure. Looks like this. What do you think makes this nucleophilic? Yeah, the pi bond in particular. So pi bonds are nucleophilic. Okay, that's the full exhaustive list of our general classes. We can either have things that are partial negative, full negative, lone pairs, or pi bonds. Let's do the same thing for electrophiles. What if we have this molecule? Why is this electrophilic? Yeah?
Why are pi bonds nucleophilic?
We're going to cover that more, but if you think about a pi bond, it's electrons in a p orbital. Those p orbitals are a little bit further away from the nuclei, and because of that, they can interact with neighboring molecules. If you've got electrons in a sigma bond, they're really tightly constrained and are less reactive than a pi bond. Why is bromomethane electrophilic?
The dipole is going towards the
Exactly. So this time our dipole is going the opposite direction, which means that our carbon is delta positive. So delta positive atoms are electrophiles. What about...
I have a question.
Yep.
So in that case, would you identify the bond as electrophilic or bond as electrophilic?
What we're looking for is nucleophilic atoms. So in the first example of our nucleophile, we said carbon was a nucleophile. This one we've got oxygen is a nucleophile. In this case, the pi bond itself is a nucleophile. Up here on our electrophile side, now we're saying that carbon is an electrophile, not a nucleophile. All right, the second example, why is this electrophilic? It's got a full positive charge on it, right? Oops.
So are you always looking at the central carbon as opposed to looking at the lithium or the bromine?
Yeah, in this case, you could say, well, lithium's got a positive charge. Lithium could be an electrophilic site, but it's not going to be a nucleophilic site, right?
Right.
So we always have to ask ourselves, what are we looking for, a nucleophile or electrophile? And nucleophiles always have some form of negative character on them. Electrophiles have some form of positive character on them. All right, the last one. Whoops. Trusty one from the exam you guys saw. Oops. I think this was on one of the exams, right? Boron trifluoride. Why is this electrophilic? Yeah, it's got this empty p orbital that's sticking straight up and down. So we can just say vacant p orbitals also make molecules electrophilic. So these are our general guidelines. You'll see nucleophiles and electrophiles nonstop for almost every single reaction. But what we are going to do is we're going to practice a little bit. So I've got an example problem. And I abbreviate nucleophile as NU, and I abbreviate the electrophile as E+. All right, so we've got a boron here. And there we go. Let's identify our nucleophilic site, electrophilic site, and try to complete this reaction. Where's our nucleophilic site? Next to lithium? Why do you think the carbon next to lithium is going to be our nucleophile? Yeah, exactly. So it's hogging the electron density from lithium. Therefore, this is our nucleophilic site. In fact, this bond is so polarized, oftentimes people will even show it as ionic. So let's just show it as ionic. What I'm going to do is draw this in as a lone pair. So it's stolen those electrons from lithium. Now lithium's positive. And then where's our electrophilic site? On boron. Okay, so we can go through and we can say, all right, boron is our electrophilic site. Why is boron the electrophilic site? Yeah, the empty p orbital. So now what we need to do is we need to do reaction arrows and show the product of this reaction. So what's attacking what? Yeah, the electrons from our nucleophile are going to get dumped into this p orbital on boron, and I want you guys to try to help me draw this product. What's it going to form? Yeah, a ring, right? And our ring specifically is going to be 1, 2, 3, 4, 5. So it's going to be a 5-membered ring. One of the vertices will be boron. You guys are going to be artists here shortly, whether you like it or not. There we go. That's not a good artist rendition. Let's do that again. Yeah. Don't learn from me. Take some art classes. There we go. All right, so we've got our 5-membered ring. What are we missing? Well, the methyl is off of the boron, and then lithium is just hanging out, doing its thing. Are we done? Oh, what's not right? Negative charge. See, we got to keep track of our formal charges. Now we've got boron with a negative charge, but we were able to predict the reactivity of this molecule just by identifying its nucleophilic site and its electrophilic site. All right, what we're going to do tomorrow is when you guys come in, I'm going to have a worksheet on different types of arrow pushing, and we're going to work in small groups, and we'll also go over the quiz.